Welcome to a chemistry lesson. Today we're going to talk about the equilibrium constant. The overview of this video. First, we're going to talk about what is exactly at equilibrium. Secondly, how to calculate the equilibrium constant. And thirdly, examples and what does it tell us. So first, what is at equilibrium? Equilibrium is when the rate of the forward reaction, the arrow going this way, producing C and D, and the rate of the reverse reaction producing A and B are constant. For example, we have this concentration versus time graph. So at first, if we have a rigid container and we put a number of reactants inside the container, the reactants are going to start to react and we are going to produce products over time. And as the reactants produce products, they eventually reaches an equilibrium point. This is when the rate of the forward reaction and the rate of reverse reaction remains constant. Second, how to calculate the equilibrium constant. For the equilibrium constant, it's often just called KEQ, or just K. To find K, we need the concentration of products raised to its coefficients over the concentration of reactants raised to its coefficients. Example from before, A plus B yields C and D. To figure out the equilibrium constant K, we need the concentration of products, which is C and D. So concentration of C raised to its coefficients times the concentration of D raised to its coefficients over the concentration of A raised to its coefficients times the concentration of B raised to its coefficients. However, if we are working with a gas, over here, gas, then we use something called Kp. So instead of concentration of products or reactants, we use the partial pressures of the product and reactants. So for Kp, in this case, the partial pressure of C raised to its coefficients times the partial pressure of D raised to its coefficients over the partial pressure of A raised to its coefficients and the partial pressure of B raised to its coefficients. Some things to keep in mind when we're doing the concentration or the partial pressures. The concentration is measured in molar, which is moles per liter. So if a problem gives us the grams of a reactant, then we need to convert it to moles. And if it gives us like milliliters, then we need to convert it to liters. And for the partial pressure is measured, the standard condition of pressure is ATM. So if it gives us anything other than ATM, then we need to make sure to convert to ATM before we plug it into the reaction. Let's look at an example. Silver dioxide reacts with oxygen gas to produce silver trioxide. Given at equilibrium that the partial pressure of SO2 equals 0.10 atm, partial pressure of O2 equals 0.30 atm, and the partial pressure of SO3 equals 0.45 atm. Whenever we are given a reaction, we must remember to balance it. So after we balance it, we can start writing the Kp. Kp equals the partial pressure of the products, which is SO3 raised to its coefficients, over the partial pressures of SO2 raised to its coefficients times the partial pressure of O2 raised to its coefficients. So Kp equals the partial pressure of SO3, which is 0.45 raised to its coefficients, over the partial pressure of O2, which is 0.10 raised to its coefficients, times 0.30 raised to its coefficients. So after plugging it into the calculator, we get 68 rounded to 2/6. So what does the k-values tell us? When we have a large k-value, then it favors the products. When we have a small k-value, which is like less than 1, then it favors the reactants. When we favor the products, we have more products in the container at equilibrium than reactants. When we favor the reactants, we have more reactants in the container than the products.